All right, welcome everyone. This is the ASQ Quality Management Division and Inspection Division joint webinar. Today we will talk about accelerator-based large format computed tomography for industrial parts. Our speaker is Andrew Good. Again, this is a joint presentation of the Inspection Division and the Quality Management Division. Let's learn about Andrew just a little bit before we kick it in. Andrew is the Technology Manager at the Jesse GARANT Metrology Center. He is not only the Technology Manager, but the head of the Computed Tomography Department, a globally recognized part inspection company providing NDT and metrology services using advanced imaging equipment. He's an active member of the CINDE, which is, as Andrew informed me, the Canadian version of the ASNT and ASME as well as participating in several committees overseeing the establishment of standards in industrial computed tomography. He has contributed articles for quality magazines, including How Industrial CT Supports GD&T, Mold Making Technology, Inspecting Highly Complex EDM Projects with Industrial CT Scanning, and for GrabCAD, Industrial Computed Tomography, 3D Printing's Biggest Ally. Andrew is a graduate of the University of Windsor with honors in software engineering. So, Andrew, you have the con.
Okay, thank you very much. I appreciate it. Sorry for the ugly mug there up on the screen there. It's the best picture that I've got so far. So what I'm here to talk to you guys today about is accelerator-based large format computed tomography. I don't know how familiar you guys are with using the little WebEx participant program, but seeing as we have a relatively small group here, how many people are actually familiar with industrial CT scanning? Have you guys used it? Do you have one in your plant or at your work, or do you contract to somebody? You know, it'll kind of give me an idea of what sort of user level everybody's at.
You can respond using the chat window.
Right. All right.
So we do have some responses, unfortunately, heading in the Q&A window. If you could put those in the chat window, that'd be great. But basically, we've had 2 responses, and they say no familiarity whatsoever.
Okay. So, when it comes to industrial CT, it's a very, very powerful tool. Here at Jesse GARANT Metrology Center, you know, we're an independent service lab, and we have machines basically ranging from 80 kV up to 3 MeV. Now, for those that don't know, that may not sound very impressive, but it's a fair number of machines. So I guess what I have to do is basically explain what we are, why use computed tomography, and why we use what we use. Okay, so basically, here at Jesse GARANT Metrology Center, we're here to try to help create meaningful advancements in industry. I know that's a term coined by our marketing department that I'm supposed to use, but essentially what it is that we're a non-biased source. We aren't out to sell you a machine. All the machines that we have are purchased from other vendors and then customized by us to basically service our customers. Now, why would you use us? Well, we have extensive experience when it comes to industrial computed tomography. We've scanned over 15,000 unique parts. Now, that's not total number of parts because that number is up into the hundreds of thousands, but unique parts over 8 years. We've seen this industry grow and adapt and basically change over the years. And basically, we're here to try to service that and to help educate people on the power of CT. So, in order to explain a little bit of some of the larger size machines, is that we ended up having to expand and build a new facility. When you start getting into the millions of electron volt machines, you need a fair amount of shielding and space. So what we ended up doing is purchasing a building of approximately 15,000 square feet. And here to process all that information with all our machines, we have 7 different analysts, and we use volume graphics to basically perform all of our analysis. Okay. So why would you want to use computed tomography, and what is computed tomography? Well, I mean, the actual concept of computed tomography is actually relatively simple. It's basically based on 3 components. You have an X-ray source, you have a rotary table that is in relation to part placement, and then you have a detector. So basically the X-ray shoots through the part, is read by the detector. Okay? And then what ends up happening is as you can see on the screen, you place the part in the path of the beam, which is then picked up by the detector, and as it rotates over a 360-degree arc, what we end up doing is capturing several thousand projections. And then once those projections are captured, we run a mathematical algorithm called a Feldkamp or backscatter algorithm to create a 3-dimensional model. Now that you have a little bit of understanding of what CT is, anybody that actually has machines, when you start getting into something that's into the millions of electron volts instead of thousands, you need a lot of shielding. So to get into the real meat and potatoes of it is that our vault, we built a custom-made vault to serve exactly what we need. Now, to give you an idea, the walls are over 6 feet reinforced high-density concrete, and the whole vault weighs over 1.8 million pounds. Just the door alone is a 4-inch thick solid piece of steel that weighs over 14,000 pounds. Apparently my mouse is being a little goofy here. Okay, now we have this big vault. Now we got to stick a detector in it. So we ended up deciding to go to a custom route because historically, in the past, the only types of detectors that were available for the MEV range were more or less 16-inch panels. You can see me there holding one up. Or LDAs, which is a single line of pixels. Okay, so our custom-built panel, it had to have certain requirements. So basically, we wanted a high resolution. So it's approximately 1 meter by 1 meter. It has a 500 micron pixel pitch with an effective pixel matrix of 2K by 2K at 16-bit. Now, for expandability, we decided that we were going to shield it a little bit more than what we needed. So we decided to shield it up to a 6 MV. Okay. But unfortunately, there's always problems when you have custom-built solutions. And basically, due to the size and the nature of a linear accelerator, we were getting something what's called a barrel distortion, which is basically the center of the panel is reading. It's basically a fisheye distortion. Okay, so basically what we ended up having to do is create our own correction algorithm to compensate for that barrel distortion. Okay, then we started getting into the actual testing. Okay, so as I had mentioned earlier, here at Jesse GARANT Metrology Center, we use volume graphics exclusively. We're a volume graphics house. So we had to make it so it was compatible with volume graphics. So we use that software to reconstruct and analyze all of our data. What you're seeing here on the screen right now is actually a ceramic radar dome from, how do I put this? Something that's dropped out of a plane. Okay. Now, the thing is why should we be using a LINAC? Well, the big thing is with a LINAC, you have huge amounts of power. Huge amounts of power. And anybody that's used CT before, the higher the density of the material means the less penetration of the energy or of the photons through the material. And basically, as the photons try to pass through the higher density material, it gets absorbed. But with a LINAC, you're accelerating the energy at such a point that you're actually getting more photons through the denser material. Okay? And what we're able to do is you can actually see the different components within this particular test piece. Yes, I know it's a little power washer, but basically you can see the interfaces between the multi-material. Okay, that's something that you traditionally couldn't do with a sub-MV range. Okay, so basically you can see everything inside this particular test piece. So you can actually strip away the low-density components and leave just the high-density components. I mean, you can even go as far as to see the plastic next to the metal, next to the aluminum, to the brass, and even see gasoline in it. You know what, since we're such a small group, you know what, feel free to ask any questions as I'm going along here. We'll make this a little bit more interactive.
I'll go ahead and unmute, and let's see what happens.
Absolutely.
Okay.
Okay. Another major benefit of using a linear detect or a linear accelerator is that with a sub-MV range, you're not always seeing the full picture. Now, what you'll notice is an image on the left, which is done using the accelerator, and an image on the right, which is done using a 450 kV source. And what you notice is that there's these areas inside the battery cells that you can actually see in the accelerator. But on the 450 kV maxed right out, you can't see that. Albeit, yes, you do lose a little bit of spatial resolution, but you're actually able to see the full picture. Okay? Now, the thing is when it comes to CT, everything comes down to attenuation or penetration, depending on how you want to say it. So, in order to properly image something, you need to get through it. Okay? And everybody has parts that are larger, bigger, more dense, that really aren't a fit for traditional CT systems. And that's why we decided to make the move to a linear accelerator. So basically, a lot of the scattering effects that you see on lower energy systems are less prevalent on the accelerator. It's because basically as you're going through it, it's actually being knocked the best way of really putting it. Basically, the energy of the photons increase, the probability of interaction drops. So there's less photons being absorbed, and any photons that are being absorbed are knocking the electrons off in the direction of the panel to help image. Okay? Now, this is a question that I get asked all the time, is traditionally, LDAs have been the go-to and are the cleanest forms of detectors for accelerators. Okay. Now, taking that into consideration, I do fully and wholeheartedly agree that an LDA, or linear detector array, is more efficient. It has better signal to noise and it is cleaner. However, it comes at a great cost of time. For those that don't know, but the process of linear detector array is the part rotates 360 degrees and you still need to capture all those projections. But then what ends up happening is after the full 360 degree rotation, the LDA moves up whatever the size of the slice. So if you have a 0.5 millimeter detector, then it moves up 0.5 millimeters and then rinse and repeats that whole process. Now, your typical LDA of running a particular part like this at 3200 projections for a full 2K matrix at 0.5 millimeter slice, okay, ends up taking 22 hours using a traditional LDA. Okay, with the DDA or flat panel detector, we can get it down to less than 27 minutes. Okay, so it's mainly geared towards faster results. Not always better, but definitely a lot faster. Okay, so that's great. What are we going to do with it? So once the data has been captured and reconstructed, there are multiple different things that we can do with this data set, okay? So the first and foremost is measurements, okay? So CMM. So basically using the power of volume graphics, what we're able to do is we can perform full first article inspections. So what the process is you end up taking a particular drawing, you balloon it, and then using the volume graphics software, you translate that into the actual software the same way you would creating a CMM program, but just done virtually. So basically what it allows you to do, a little noise there, what it allows you to do is actually create a full CMM template all based inside the software with tolerances. Now, the beauty of this is that you're able to actually see how the measurements are made and where they're taken, okay? So you can actually see when, you know, a line is fitted between two bosses and then dimensions. You can actually see that. It gives your engineers tremendous amounts of power. Now, not only that, if anybody has adopted the PMI in their CAD files or part measurement information in their CAD files, that can be directly imported and overlaid on top of the CT data set as well. So in this particular example, this particular part had over 1,400 measurements with 3,900 geometry elements. And the total time to apply that took 80 minutes once the template. From scan to application to report takes less than 80 minutes. Okay. Then we start getting into the wall thickness, which is usually a very important type of analysis for all different types of industries. So basically, it does exactly as it sounds. It takes the thickness of every wall throughout the entire piece and measures it. And basically, you can tolerate it, and you can say, okay, if a wall falls below a minimum thickness, it'll automatically flag that and let you know where it is. And you can actually take a look at it, and you can jump to that location, and it'll tell you. It'll give you the ability to disregard it or consider it as a non-conformance. Okay? Voids and inclusions. I have to say that this is probably the most popular type of analysis that majority of people that use CT run. So with void and inclusion, basically what it does is it searches the entire part for voids, which are low density, or air pockets contained within the material, or inclusions, which are high density particles contained within the actual part. So the thing is with both void and inclusion analysis, what it does is it gives you the ability to find out where your voids are, determine if they're in high stress points or critical areas. And then what you can actually do is you can actually take that information and input it and share it with magma or mold flow to help adjust your process to minimize the amount of voids created during the process. Feel free to ask any questions as we're going.
Andrew, Jeremy from Des Moines.
Good afternoon. What's your question?
I deal with ball grid array inspection with solder paste through a surface mount technology, and I look at voids through an X-ray beam right now, but I'm not able to capture 3D voiding or anything like would that apply to that as well?
Absolutely. So basically, void or solder, or lack of solder in BGAs, CT is a fantastic tool because you can actually classify and see how much void there is. Because, as you know, when you're looking at a radiograph, I'm assuming you're probably doing it in an oblique.
Yes.
That's great, but it doesn't give you a true sense of depth. And that's where CT is fantastic, because it'll actually give you that depth. It'll tell you exactly where it is, and it's somewhat automated, where traditionally if you're using regular X-ray, there's no indexing.
Okay.
Okay. Now, this is a nifty little feature that has been added to volume graphics that really works well with our accelerator is textures. So once a CT data set has been scanned or reconstructed within the software, what we're able to do is we can actually merge white light data with texture information and overlay it. Okay. Now, this what you're looking at is actually a dinosaur head. Looks more like a rock, but I'm told it's a dinosaur head. Well, what that actually means is that in order for any measurement to be trusted, it needs to be correlated. Okay? And traditionally in the past, most CMM inspection has required scribe lines to make sure that everybody is taking the measurement at exactly the same location. So with the inclusion of textures, what we're able to do is overlay that texture information on top of the CT scan. So that way we can match apples to apples. So that way we know exactly where the part needs to be measured. So that way we can correlate that back. Okay. Additive manufacturing. This seems to be the new thing. Everybody wants more and more information on additive manufacturing. Unfortunately, what ends up happening is that everybody seems to be printing denser and denser materials. And I know a lot of people usually end up printing different types. You've got sintering, powder bed, all these different types of technologies. I apologize if I'm not fully up to date on the different types, but we're starting to see more and more types of 3D printed parts, and majority of the ones that are coming out are usually either titanium or a super alloy like an Inconel or cobalt chromium. But the problem is when you start creating a structure with it, how do you know if you have powder trapped inside some of your channels? Not to mention, what's the geometry of those channels? You know, because unfortunately, as anybody that 3D prints knows, is that it's not very smooth and it's not very consistent. Okay? And this is where CT is extremely powerful. What you're able to do is you can actually see the unfused powder contained within the part. Okay? And you can actually see how uniform the walls are and the internal passages. Okay? Inconel. I have a real love-hate relationship with Inconel here. So, for those that don't know, Inconel is a super alloy. It's very dense and it tends to absorb X-rays. So you need tremendous amounts of power in order to penetrate Inconel. Now, there's real interest in the aerospace community with 3D printed Inconel. And what you're seeing here is a particular example. And this is where accelerators come in, is because accelerators have that energy to punch through. Now, it does tend to cause some issues because I know everybody wants, you know, less than 1 thou resolution and everything else, but we have to be realistic on what we can actually achieve. Okay? If you give me a part that's, you know, if you give anybody a part that's, you know, 16 inches in size, you can't say that you want 2 micron resolution. It just doesn't happen that way. It's physics. There's no technology that will allow you to do it. If you wanted to measure a flat plate, CT is not your answer. You know, that's a CMM. But if you want to actually see meaningful results, i.e., you know, within 200 micron, 250 micron, then CT is really your answer because it will, in a single data set, capture not only voids, but wall thickness, measurements, inclusions, structural analysis, fiber analysis. Every type of analysis can be run off a single CT data set after capturing. Okay. So, I mean, the real advantage for using CT, especially with a DDA, is it's fast acquisition time and scan time. With a 1 meter panel, it allows you to have a large field of view. Shorter scan times equal less wear and tear on the equipment. Okay? And not to mention, it's slightly more versatile than a standard LDA because there are several different types of tricks that you can perform with a flat panel that you can't with an LDA. And one of the main reasons to use an accelerator for computed tomography is clean differentiation between mixed materials. Plain and simple. High level of resolution and accuracy within reason, of course, and large density and low density materials that cannot be scanned using traditional tubes. Now, if anybody has any questions, I'd be happy to go through it because I can actually go through and show you in real time what an example looks like.
Yeah, that'd be great.
Anybody have any questions before I jump over to a real example?
All right, you're getting lots of positive feedback to jump into the example.
Excellent. Okay, so what you're seeing here is a large part. I was scanned using the accelerator. Okay. And what it is I apologize for not explaining this a little bit more in detail earlier, but basically what we're capturing is what's called a voxel-based data set. What a voxel-based data set, for lack of a better word, is a 4-dimensional data set. So it contains X, Y, and Z information in addition to density information. So what that allows us to do is we're able to pinpoint and locate changes in density. Okay, so what you'll notice here on my screen as I scroll back and forth is you have large pockets of voids. Okay. Wall thickness. Curious about a wall? Not a problem. It'll tell you the thickness of every wall. We have full tolerancing. Okay. So if we want to find a particular wall that's, say, less than 2.5 millimeters, all of a sudden we now have a red indicator showing that we have something that has fallen out of tolerance. When we click on it, it'll jump right to that location. So basically what it's signifying is it's working in concert with the actual void analysis to let us know that we have a compromised structural wall, that basically the thickness of that wall has been compromised by porosity. So it's no longer a valid thick wall. Anybody have any questions while I'm running through this?
There is a question. Adrian has asked, how big the samples must be in order to measure with a CT scan? Is there a range?
Okay, so with CT, you can scan objects as small as 100 micron in size, all the way up to several meters in size. I mean,
I think I mean sample size, not necessarily geometric, but sample sizes, I think. Mm-hmm. You said inspection, that this was used in first inspection, right? I'm just trying to make sense of the comment. I think what you're saying is I've misinterpreted the question, and you have answered it, correct?
Okay. Okay. So, as this is kind of a webinar relating to measurement, to quickly show you how powerful CT is for measuring. Okay. So, what we're able to do is you're so easily able to create dimensions. Okay.
We have to take deal with our stuff. We have to get off ourselves. She didn't say nothing like that.
So what we're able to do is you can actually see all the measurements and how they're taken and where they're taken at. Okay. So basically what we're able to do is we can create full measurement templates. And then if we wanted to apply that, let's apply that same template that was created on the next part. And it takes that long. Okay. It has the full gamut of GD&T controls as for the ASME Y14.5.
Yeah, I mean, they included like 15 and stuff like that, so like a little extra. That's why that's
Okay. Any questions on measurements at all? Okay. For those folks interested in doing reverse engineering, okay, the beautiful part about computer tomography is you can easily create, once your part has been scanned, you can create an STL from it. Okay. So what we're going to do is we're going to do a fast little STL. So basically, you can create a full STL containing not only void information, but all the geometrical information as well. Then you can take that into your CAD program of choice, SolidWorks or NX or ProE, and analyze it there if you have already pre-set up finite element analysis or your FEA. What ends up happening is we're able to create, using CT, an exact duplicate. That contains all features, not external. I can take a couple more questions, or if anybody would like to see something in specific.
I do not see any questions.
Do you have any examples where you can take apart the layers of, say, an IC chip or a processor after scanning?
Believe it or not, I don't have one handy, loaded.
Okay.
If you want, feel free to contact me afterwards, and I can provide you with a couple different examples. But not on hand.
But if I understand you correctly, we would have that capability, though, to be able to scan an object and then peel layers off non-destructively for whatever reason, for inspection or for forward or reverse engineering, I guess.
Yes, absolutely.
Okay.
And you raise a good point, Andrew. I mean, you're going to give your contact information, and if people have questions, you know, they can certainly reach out.
Yes, we're always available for questions. I mean, that's pretty much what we do here. Is that you know, we're here to educate and help further the whole community, because I firmly believe that CT is a fantastic tool. Not the right tool for everything, but it does do most things, and it does most things extremely well.
All right. As there are no further questions, I would like to go ahead and end today's webinar. As far as RUs, that will be sent out to the people that registered and attended. It's automated. You should receive it within 24 hours. And there's the thank you screen. And if you have any questions, do you have what's your email, Andrew? Do you want to put up some contact information? Is that on the front? There you go. There's the email.
Feel free to contact me.
All right. Well, thank you very much, Andrew, and thank you everyone for attending. And that is it for today.
Thank you very much, guys. I appreciate you guys having me. And if I can be of assistance in any way, feel free to contact me.
Thank you.
All right.
All right. Thank you very much, guys.
Thank you.
Everybody have a great day.